The force as a function towards analytical graphic statics for spatial structures. The motivation of this work is Maxwell's reciprocal construction for planar trusses, its extension to 3 dimensions, and the corresponding stress function for frames. The long-term goal of the presented work is to have a dimension-independent description that explains what is happening with the mechanical quantities involved at each step of this method. A non-dimension independent description is already known in the planar case. That is what I mean under analytical graphic statics. One can realize that in the plane all forces are describable with 3 numbers, the 2 components of the force, and its moment with respect to the origin of the coordinate system one chooses. In light of this, one can draw a 3-dimensional force diagram where equilibrium is represented by arrow continuous chains. As there is an exact measure in all dimensions of the space, this diagram is stricter than the polyhedra Maxwell used, but also more information-rich. One can also take the dual of this figure, if it is imagined in projective space, mapping vertices to planes. These planes can be thought of as evaluations of linear functionals over appropriately chosen projective homogeneous coordinates. The function value is the moment of the force with respect to the point. The moment diagrams appear between the respective planes. This affine description will not generalize, but the moment functional can be treated as the 2-dimensional case of the dimension-independent stress function. In order to have a dimension-independent description, recall that the force can be thought of as a vector pair or a bivector in all dimensions. The vectors are appropriately chosen projective homogeneous point coordinates representing the point of attack, and the force vector corresponding to a point at infinity. Dually, motions can be thought of as 2 forms or alternating bilinear forms, where each functional represents a hyperplane, and the motion is the product of 2 reflections with respect to these 2 hyperplanes. Reflections span the Euclidean group. A moment equation, the effect of the force causing such a motion, is the evaluation of the bilinear form over the pair of vectors. Technically, this looks like a 2x2 determinant calculation. The 2 dualities used will be the aforementioned vector functional duality and the Hoche dual of multilinear forms. The latter maps a d-1 form to a 2 form, and an oversimplified view of it is that the dual will contain all the functionals missing from the primal, multiplied by -1 depending on the number of permutations required to bring the list of the 2 functionals, 2 forms to lexicographic order. Under these 2 dualities, the bivector's force will turn into a d-1 form, while the 2 form of the motion will turn into a d-1 vector. The moment equation is the evaluation of the d-1 form over the d-1 vectors, which technically looks like a determinant calculation sized d-1 times d-1. Geometrically speaking, the axis of the moment equation can be given as an intersection of 2 hyperplanes and the span of d-1 points, and the 2 formulations correspond to these 2 cases. This d-1 form or multilinear function will correspond to the stress functions of graphic statics and the force diagram, while the bivector formulation will correspond to the form diagram. For the form diagram, I am proposing a graphic idea that is slightly different from the one Maxwell used, but this has the benefit that the graphic idea will be the same for the 2 diagrams. We will identify the space of projective homogeneous coordinates with the Euclidean parts of the d+1 dimensional projective space and draw the vector pair as 2 points. According to the usual description, the finite points of d-dimensional projective space correspond to the affine subspace having glass coordinate 1, while points at infinity will correspond to vectors having glass coordinate 0. Properly choosing representants will require the 2 vectors of the bivector to be multiplied by scalars, and these 2 points will then span the line that gives the edge of the polyhedra. The projection of this polyhedra centrally through the origin will give the form diagram in the image space. Interestingly, Felix Klein used the same algebraic idea when describing the Lorentz group. The force diagram will have the same idea. To each force corresponds d-1 functionals that can be drawn as points in Rd+1. These points and the origin span a d-1 dimensional oriented volume, which can be thought of as representing the magnitude of the d-1 form. The projection is parallel with the d+1 direction, which is the same as Maxwell used. The claim is that this change in volume cancels out the moment components from the magnitude, allowing the force components to be represented by the projected volumes that are additionally orthogonal to the force vectors in Rd. To see this, one can carry through with the calculation of the presented dualities and note that as the force vector corresponded to an ideal point, the force components of the d-1 form will correspond to volumes not having a volume in the d+1 direction. Assuming the force pointing in the x1 direction gets a solid not having an x1 directional component, which shows the orthogonality. The moment components will correspond to volumes where one has to leave out two directions lying in the d-dimensional space, the image space. The pure moment would cause a rotation happening in the plane spanned by the two left-out vectors. This completes the claim and gives an exact interpretation of the basic elements of the dimension-independent graphic statics. The full utilization of this is yet to follow. Thank you very much for your attention.